So this week we're going to have a look at a technique that gives us a way of solving ODEs that we haven't really seen before, particularly ones that have a discontinuous forcing function. This technique is called the Laplace Transform, and it's widely applicable beyond the realm of ODEs and things. So if you carry on in physics, this is generally going to be a useful thing to know about, even if you don't use it for solving ordinary differential equations. So just to kind of put into context why we're doing this, so far when we've looked at non-homogeneous differential equations, we've pretty much looked at ones that always have a continuous forcing function. So we're thinking about non-homogeneous ones, and the forcing function is the term that only has, for example, t in it, no u's. So if we look, for example, at this dE over here, the term that doesn't have a u in it is a 6, so that just has a constant forcing function. In this dE, the second order dE over here, our forcing function is a decaying exponential. So we're thinking of these, if you kind of are thinking in terms of physics, as external forces that are applied to the system. And so far we've only really looked at situations where those external forces are continuous. But we can think of many situations where we might need to have a discontinuous forcing function. So to step away from a kind of physics look, we could go back to drug absorption. So we talked about intracochlear drug delivery. Another area of medicine where ODEs are quite important is modeling drug absorption within the body. So after major surgery, typically, obviously, you don't want the patient to be in pain when they wake up. So one standard way of providing the drug is to give the patients a sort of a hefty amount of morphine straight away, one single dose, and then possibly give an intravenous drip at a lower level, but there's this kind of initial dose, and see how the patient does. And then after a while, for example, if the patient is saying that they're in a lot of pain, they might need another single big dose. And you can imagine that if you're trying to model this, now suddenly you have discrete things that are being added to the system. So we might want to model how drug absorption works in a situation like that. So if we let u of t be the amount of the drug in the body at time t hours, and we're going to just let k be a positive constant with units 1 over time, then using the same reasoning that when we talked about the intracochlear drug delivery, we can use this model which says that the rate of change of the amount of drug in the body must just be given by the rate at which the drug is going in less the rate at which it's going out. And here we've said that the rate at which it's going out is based on how much is in the body times some kind of absorption coefficient type thing. So it's this rate that's going that of the drug going in that is kind of acting like our forcing function here. It's the thing that we determine. So maybe if your person is on an IV, then and they're just having a constant flow, that RT might be just a constant. But you can also imagine that you give them a single big dose, in which case this R of t looks a bit different. So for example, as I've just said, if we've got a continuous drip, then you might have that your R of t is just 1.5 milligrams per hour. But if at time 12 hours after the operation, the patient is in a lot of pain, it might make sense to just give them a big injection, in which case really what your R would look like in that case would be something like this. So it's a function which is 0 at all the time except at time t equals 12 when it's 10 milligrams. Another thing that might happen is that your patient is on a continuous drip which starts off at a certain level, 1.5 milligrams per hour for example, but it turns out that the patient's in a lot of pain, so at 12 hours you just increase the rate at which the drip is feeding through. So after that, the rate at which the morphine enters the bloodstream is going to be higher. So if you look at both of these over here, these give us forcing functions which we don't really know how to deal with. All the techniques that we've looked at so far have kind of required continuous forcing functions, and generally forcing functions that we know how to integrate, like causes and sines and e's. So if we want to look at any kind of differential equation of this form, where our forcing function is discontinuous, we need a technique for that, because nothing we've done so far will deal with that. This is the one thing that we need to do. We need to find a technique for how to solve DEs like this. But what we also need to do is find a way of describing these discontinuous functions in a mathematically useful way. Because at the moment we've just kind of described them as piecewise functions and there's not a lot that we could do. So we're going to start with having a look at the technique, and then when we get to the right moment we will talk about how we describe these. So the technique that we're going to use is called the Laplace Transform, and it's not immediately obvious why you might want to do this, but it turns out to be super useful. So bear with me. It's going to seem a little strange, but as I say, it does work. So the idea is that we're going to transform our differential equation into something that we can solve more easily. And we're going to do this by a kind of cunning change of variables involving integrating both sides of our differential equation. But before we actually get there, we're going to just define what it means to take the Laplace transform of a function. Now, you are actually very used to transforming functions. Every time you take the derivative of a function, you are basically applying a transformation to it that results in the derivative. If you integrate a function, then you're applying a transformation to that function that gives you a new function. So in the same spirit as that, we define the Laplace transform of a function f of t as this crazy bunny over here. So we take our original function, our f of t, and we multiply it by e to the minus st, and then we integrate the whole thing with respect to t from 0 to infinity. Totally not obvious why we would want to do this. It just turns out to be really handy. So the thing to notice within this, we are integrating with respect to t. So all our t's will disappear. We will end up with something that doesn't have any t's in it, but what it will have in it is an s, and that becomes our new variable. So we take a function which is a function of t, like we've got over here, and we do this Laplace transform, and we end up with a new function which is some function of s. Usually s will be a real number, but if you do this in other contexts, it might be complex, which can be useful. So a few words about notation. If we have a function f of t, then once we've transformed it, we'll usually refer to the transformed function using a big F. So a little f for our kind of time domain function, the one that we start off with, and then a big F of s for our Laplace transformed function. There's also alternative notation, and we're going to use both because sometimes it's more helpful to do this. So alternatively, you can indicate that you are applying a Laplace transform to this function f. So you say, I'm applying this in the same way that you would write d by dx when you're applying the differential operator to an f. And then that's also our Laplace transform. So our two notations are either just a big F for saying we've taken the Laplace transform, or if we want to make it explicit that we are taking the Laplace transform of a specific function, little function f, then we'll just use this curly L. And I'm going to use these interchangeably to try and show you where it's useful to use one or the other. Okay, so let's just do some examples. So we're going to start by computing the Laplace transform of the function, the super simple function f of t is equal to c. So this is just a straight line function. So we're just going to work through a couple of examples and get to the point where we might see how we use this with solving ODEs, but we're not there yet. We're just doing the simple stuff. So the first thing I hope that you notice over here is that this is an infinity. So this tells me that this is an improper integral, which means that we have to do the whole applying limits things. So go and revise your calculus if you're feeling a bit hazy. but we're just going to go straight ahead and do this. So we have our f of s is equal to, so the way that you handle a limit at infinity is you say, well, I'm going to take the limit as I use big T goes to infinity of 0 to big T, c e to the minus s of t dt. And we can just go ahead and do this. So I haven't worked out my limit yet. I'm just going to integrate. So this is a constant times e to the minus st integrated with respect to t. So as far as this integral is concerned, s is a constant. So when we integrate that, we should get a minus c over s times e to the minus st, and we're integrating that from 0 to t. So let's plug in our limits of integration. So we're going to get minus c over s e to the minus s big T minus minus, so that's going to be a plus c over s e to the minus s times 0. Okay, so let's just do a quick look at each of these terms. So s times 0 is 0, so this is e to 0. So this term becomes 1, so this is just a c over s. So if now we've actually got to the point where we can deal with our limit. So I'm going to do this in excruciating detail this time round, and then we'll go a little bit quicker the next time round. So I'm going to have the limit as t goes to infinity of minus c over s e to the minus s big T, plus the limit as t goes to infinity of c over s. All right, so let's have a look at our first term over here. So the t that we've got is sitting in the exponent here. So we're looking at e to the minus s big T, and then we're letting the limit go as t goes to infinity. So we have to think about two possible scenarios here. We haven't said anything about s, whether it's positive or negative. Now if s is negative, then this whole term would be positive and heading off to infinity. So we wouldn't have a convergent integral here. On the other hand, if s is positive, then we've got a negative because we're letting t go to positive infinity. So we've got minus times a positive, which is minus. So we're heading off to minus infinity, so it converges. So we only have a solution for s is greater than 0. And in that case, this term over here, the limit will tend to 0 because this is a decaying exponential. Just remember, that's a decaying exponential that does something like that, so it tends to 0. So this term tends to 0 if s is bigger than 0. So finally we're just left with this term over here. Now if we want the limit as t goes to infinity of c over s, well, there's no t in there. It's always going to be c over s, it doesn't change. So our final solution is c over s. Okay, so this is the strange Laplace transform. Again, we're just learning this weird thing, haven't figured out why yet. So this says that if you start out with a function that is just a constant and you find the Laplace transform, what you get is that constant divided by s. So notice that we start out with a constant function here. So this is a constant function. But what we end up with is not a constant. It depends on s. Okay, so that's the Laplace transform. Let's do another example. So here we have the function that we are looking at is e to the 3t. So we can go straight ahead again. Don't forget, improper integral. So we've got to do the full works with limit as t goes to infinity, integral from 0 to t, e to the 3t minus st dt. So I just included those together, and I'm actually going to rewrite this as 3 minus s times t. Okay, so that's a pretty straightforward integral. We know how to do that. So we've got limit as t goes to infinity of 1 over 3 minus s e to the 3 minus s t from 0 to t. So let's work this all out. So I'm going to split it up again. I've got my limit as t goes to infinity of e to the 3 minus s big T over 3 minus s minus the limit as t goes to infinity of, so this is going to be e to the 3 minus s times 0, so that's e to the 0, which is just 1, so it's going to be 1 over 3 minus s. And we do the same thought process again. Now, in order for this term here to converge, we need to have that 3 minus s is negative, because otherwise we're going to have e to the positive infinity, it's going to diverge. So let's just make a note here. Have a convergent integral. We need 3 minus s to be less than 0, so that tells us that we need to have s is bigger than, is bigger than 3. So for s greater than 3, why do I keep writing zeros? Okay, s greater than 3, we have that f of s is equal to, so if s is bigger than 3, then this term over here, as t goes to infinity, will go to 0, so that term goes to 0, so it's going to be 0 plus. And then for our second term over here, again we have a situation, it doesn't depend on t, so it just stays as a constant, so that's 1 over 3 minus s. So finally our f of s is equal to 1 over 3 minus s. Okay, so here we go. We've just learned how to calculate the Laplace transform. It might seem a little bit weird, but I'm pretty sure that the first time you learned to differentiate something or you integrated something, it felt a bit weird. It was just a thing you learned to do. So here we go. We've learned another thing to do. We are heading towards using this to solve differential equations, but first it's worthwhile thinking about what kinds of functions can be transformed. So if you think back to when you learned about differentiation, you learned about which functions could be differentiated and where they could be differentiated. So you had to worry about things like, are they continuous or not? So it's a logical question to ask which kinds of functions can be transformed. Now you'll notice that in both the examples that we did, we had to think about where our Laplace transform would converge, because we're taking a limit, because we've got these improper integrals. So really what we're thinking about is what kind of functions aren't going to explode too quickly, so that we have a divergent integral instead of the nice convergent one that we want. And the answer to that is we define what is called exponential order to give us a sense of the growth rate of functions. So a function f of t defined for t greater than 0 is of exponential order if we can find a constant a and m, so that if we look at the absolute value of the function, it's always going to be less than m times e to the at. So basically we can think of this as saying, can we find an exponential that bounds our function in some way? So we never have a situation where, for example, if this is an exponential, let that be e to the at, then a great function, which as far as we're concerned would be fantastically exponential, would be a straight line. That would be great because it's always bounded on top. But on the other hand, if you had some function that instead did something like this, and you couldn't find an exponential under which that function always lay, then that one would not be. So you could, this looks like it might be quadratic, and you might be able to find a different value of a which made an exponential increase fast enough. But if not, then sorry, no luck. So we're basically ruling out things that grow too fast. We want things that kind of only grow at most exponentially. So if you want an example of something fairly straightforward that is not of exponential order, if you looked at, for example, f of t equal to e to the t squared, that's not of exponential order, because you can't find a constant a, and the m isn't going to really help here, which means that e to the t squared would always be less than e to the at, because it's just going to grow. This is just going to triumph. This is always going to triumph. So there are functions which you might want to deal with, which we can't use. We can't use the Laplace transform on, in which case you need to do another technique. But we're going to mostly work with functions that are of exponential order. So the second thing that we're, in terms of thinking about what are the kinds of functions that we can deal with here, we're going to say that, firstly, in case you haven't seen it, we say that a function is piecewise continuous if it has finitely many jump discontinuities. So a jump discontinuity, you can read the technical definition over here, but the picture that you want to have in your head is that you have a function which comes along and does something like that. So it's not a kind of, it's just done one single little jump. And we're allowed to have finitely many jump discontinuities, but it's continuous everywhere else. So putting those two things together, we say that if our function is defined for t greater than 0, so that's our first condition, it's piecewise continuous and of exponential order, then the Laplace transform is defined, and it exists for all s greater than a, where a is the constant that we had in our definition of exponential order. So we said, remember, that our function needs to be bounded by some exponential like that. So that's just kind of the technical details. We won't really even think about this because the functions that we deal with meet all these criteria. But one day, if you're out in the wild and you need to figure out whether you can actually use a Laplace transform on something, you need to think about, is it piecewise continuous, of exponential order, and defined for all t bigger than 0? If yes, Laplace; if not, something else. So now we need to think about Laplace transforms for all our common functions, obviously, just like you learned about derivatives of all your common functions and integrals. So we're learning about the Laplace transforms. So one of the first things that you will have learned about derivatives, you'll remember, is that d by dx of f plus g is df by dx plus dg by dx. And you'll be glad to know that the Laplace transform behaves exactly the same way. So if you take the Laplace transform of two functions added together, it's the same as taking the Laplace transform of the first function and adding it to the Laplace transform of the second function. So that's delightful. And similarly, you will have remembered that d by dx of some constant times a function is just the constant times the derivative of the function. And again, Laplace works exactly the same way. So if you take the Laplace transform of some multiple of a function, it's the same as some multiple times by the Laplace transform of the function. Okay, so this is great. This means the Laplace transform works exactly like we would like it to, and that is intuitive for us. And we can work with combinations of functions, additions and scalings of those. And feel free to check that this must be the case based on our definition. So most often we're going to end up using this table because it gets really tedious doing these integrals. So here is a table of common Laplace transforms. So we in fact just showed this one over here, and we did an example of this one over here with a was equal to 3 or minus 3, I can't remember. And you could convince yourself that if you take the Laplace transform of some polynomial term, you get something that looks like this. We also often are going to have combinations. So here we look at polynomial term times an exponential. Here we have the Laplace transforms of our sine and cosine, which look kind of unexpected. We're used to having, with differentiation and integration of trig functions, we get back a trig function, but we don't get that here. We get some odd-looking things. And then we have combinations of exponentials and sines. So you'll notice here that we haven't started talking about discontinuous functions yet. That's a way away. We're just going to work with this for the moment. So the important thing here is also to note that we have some restrictions on our s's. So these are based on the constants in the original function that we're thinking about. So in the example that we looked at over here, we had s had to be bigger than 3. Okay, so the reading exercise 5.23 is important because it says the very important lines: use your favorite computer algebra system to verify the truth of any or all of the entries in here. So these days we pretty much use things like Matlab or Mathematica or Wolfram Alpha to calculate our Laplace transforms. It's a good idea to have done 1 or 2 by hand, and I will ask you to do a couple in the tutorial, but out in the world you just get the computer to do it. So let's use the table to just compute the Laplace transform of something a little more complicated. So here we have our function, which is a combination of an exponential, a cos function, and a polynomial term. So I'm going to write this using the funny L to say I'm taking the Laplace transform of f of t is going to be the Laplace transform of 7 e to the minus 2t plus the Laplace transform of minus 3 cos of 2t plus the Laplace transform of 2t cubed. So this was in excruciating detail. Let's just work through using the rules that we know so far. So this is going to be equal to, now this is the first term is the Laplace transform of 7 times an exponential, and we know that if we multiply some function by a constant, we can bring the constant out. So this is going to be 7 times the Laplace transform of e to the minus 2t, and again we can bring out this minus 3, so that's going to be the Laplace transform of cos of 2t plus Laplace transform times 2 of t cubed. And at this point we can have a quick look back at our table over here. I might even have this. Okay, so that's, I don't have it stored in memory, so let's just grab a copy. Oops, oh, that did not work the way I wanted. Okay, we'll just have to look back. So we want the Laplace transform of e to the minus 2t. So we have this line over here. So our a is going to be minus 2, so that's going to be 1. So we have, so it's going to be equal to 7, and we have 1 over s minus a, so 1 over s plus 2. We've got a minus 3. Now we need the Laplace transform of cos of 2t. Cos of 2t, so here we've got a b and that's going to be, our b is equal to 2 s over s squared plus 2, which is 4, so it's going to be s over s squared plus 4. And we do the same thing for the last term. We go and look up what is the Laplace transform of t cubed. It's going to be 3 factorial over s to the 4. So this is going to give us 2 times 3 factorial over s to the 4. So finally, and I'm going to change notation here, I'm going to say big F of s is equal to this crazy thing, 7 over s plus 2 minus 3s over s squared plus 4 plus, well, let's just work this out. So 3 factorial is 6, so 6 times 2 is 12 over s to the 4. Okay, so here we have transformed this function of t into the Laplace transformed version, which looks like this. Okay. So if we're going to use this for solving ordinary differential equations, then we need to do something about Laplace transforms of derivatives. So one thing that you can do, and I do encourage you, is if you have a nice function f, and by nice I mean it's suitably differentiable, and it's differentiable, and when you take the derivative, so when you get your f prime, you get the things that are necessary to be able to take the Laplace transform. So piecewise continuous, exponential order. Then we can find the Laplace transform of the derivative, and you can actually show, and I do encourage you to do this, that the Laplace transform of the derivative of the function is s times the original function, so the thing before the derivative, minus whatever that function value was at 0. So this is my challenge. Go and show this. Okay, you just need to do the integral, and it's straightforward. Okay, so we're going to do this calculation 2 ways to kind of justify that it seems to work. So our original function is going to be f of t is equal to cosine of 3t, and we want to find the Laplace transform of the derivative of f. So we could just use this equation up here. So that equation says the Laplace transform of f prime is s times the Laplace transform of our original function. So that's the Laplace of cos of 3t minus cos of 3 times 0. Okay, so let's work this out. So we've got, that's s. We want the Laplace transform of cos of 3t. So if we go back to our table over here, that's going to be s over s squared plus 9. And we're going to subtract off cosine of 0, which is just 1. So we end up with, this is s squared over s squared plus 9, or minus 1. Okay, peachy. We could alternatively, and we're just doing this so that we can check that we've done something correctly. You wouldn't have to obviously do this both ways in real life. Let's find the first derivative. So f dashed of t is going to be minus 3 sine of 3t. So we could just go straight ahead and find the Laplace transform of minus 3 sine of 3t. And using the rules that we know, we get minus 3, and we need the Laplace transform of sine, which is b over s squared plus b squared. So that's minus 3, and our b here is this, so that's b over, what did I just say? I said b over s squared plus b squared. b b over s squared plus 9, which is equal to minus 9 over s squared plus 9. And you might look at this and go, that is not the same. If we look at those, are those equal? Initially you might say no, but I would recommend that you just write this one as an s squared plus 9 over s squared plus 9, work out the cancelled terms, and you'll see that all is good. They are equal. They are equal. Yes. Okay. So this is just to show you that in a kind of very hand-wavy way, that it seems like this crazy expression here for taking the Laplace transform of some function, of the derivative of a function, is correct. So let's use this. So this is how we use the Laplace transform to solve ODEs. So here we go. So here we have a derivative, and we've got a very simple ODE. Du by dt is equal to 3 times u. Now, we could totally solve this by other methods we've already learned, but I want to do an example that is straightforward, that we know that we can look at and we can go, yes, the answer is correct. But we're going to use the Laplace transform. Okay, and we're going to have the initial condition u of 0 is equal to 5. So let's use the notation that big U of s is the Laplace transform of u of t. So what we're saying is that big U of s is equal to the Laplace transform of u. It's just going to make the notation a little bit easier. Okay, so what we do is we take the Laplace transform of both sides. We have, of course, mentally checked that we can, that the things that on either side are piecewise continuous, and whatever our other criteria were, they are. It's all good. So here we go. So we've got the Laplace transform of the derivative of u is equal to, I'm just going to take the 3 out straight away, the Laplace transform of u. Okay, so using what we know about finding the derivative, this is going to be s times the Laplace transform of u minus u at 0. So this is going to be s times u of s minus u of 0, which is 5, which is equal to 3 times u of s. Okay, so let's solve this for u of s. So this gives us that u of s is equal to 5 over s minus 3. And at this point, you should be saying, well, this is not great, because we don't want u of s. We want little u of t, and we've ended up with big U of s. But in this simple case, we can actually figure out what u of t, little u of t, must be in order to end up with a big U of s. So what u of t has 5 over s minus 3 as its Laplace transform? Well, we could just go back and look at the table. What does the table tell us? It looks like we're going to need something of the form e to the at, because we have 1 over s minus a as e to the at, so if we let u of t equal 5 e to the 3t, then that gives us the right Laplace transform. So I realize this is probably a little bit unsatisfying that we went back and referred to the table, but this is pretty much how we would do this, or we just ask a computer to give us what's called the inverse Laplace transform. So the inverse Laplace transform will take a u of s and it will spit out a u of t. So notice that we didn't actually end up doing any integration here. Because of what we know about the Laplace transform, we just basically turned this into an algebra problem. The algebra problem appeared over here where what we really needed to do was solve, well, sort of over here, we solved for u of s, and then we needed the inverse Laplace transform. Okay, so this shows you basically how one solves ODEs using the Laplace transform. So one takes, so we start here, and you take the Laplace transform of both sides. So you end up with something that just has Laplace transformed versions of the thing that you're looking for. You do a bunch of algebra so that you end up with a formula for your u of s. You take what is called the inverse Laplace transform and you arrive at your solution. And at the moment that's probably looking like a lot of work. In the case that we've just seen, you could have just gone straight to the solution using one of the techniques that we know already. But in cases where you don't know how to go straight to the solution, the Laplace can help. So let's just have another look at a slightly different problem. Maybe we can use the Laplace transform for second order differential equations, and we can for homogeneous second order examples. And again, you can check for yourself that the Laplace transform of the second derivative of a suitable function will look like this. So you'll notice that it again has a term that includes the Laplace transform of the original function, and then it includes the value of the function at 0 and the value of the derivative at 0, which is kind of what you might expect. So let's have a look at this example. So we're going to take the Laplace transform of both sides. So we've got the Laplace transform of u double dashed, and I'm just leaving out the t's because it's getting boring writing those. I've got 4 times the Laplace transform of u dashed plus 3 times the Laplace transform of u is equal to the Laplace transform of 0, which is 0 over s, which is 0. So that's 0. Okay. And now we just read off from our definitions. So the Laplace transform of the second derivative will give us an s squared u of s minus 2s minus 4 plus 4. So now we've got this here is going to give us a 4s times u of s minus 4 times 2, because we've plugged in this value here. And then finally, we're going to have plus 3 u of s, and this is all equal to 0. So these two terms came from plugging in my values for u of 0 and u prime of 0. So if we work this all out and do the simplification, what you would get would be that our u of s is equal to 2s plus 12 all over s squared plus 4s plus 13. So back in the old days, before we had computers that could kind of solve this for us, what we would do would be to use partial fractions. So you could use partial fractions, in which case you would get u of s is equal to 5 over s plus 1 minus 3 over s plus 3. And then you could go back and look at your original table and say, well, this must be that our little u of t is 5e to the minus t minus 3e to the minus 3t. So using the same technique that we did before, we went and looked at the table and said, what gives me this and what gives me this? And the answer is those. Partial fractions is a pain. We don't really want to do that, so mostly we just use Matlab. Or whatever your favorite computer algebra program is. So if you want to go in and give this a try, if you have a look, so MATLAB, here are the MATLAB commands. You can do this in Mathematica, you can do this in Wolfram Alpha. I think Symbolab will also do this. But basically, you need to define, so here we're looking at our function x of t is equal to t, so a very straightforward function. If we want to take the Laplace transform of that, there's our f. We're going to define some symbolic, so sorry, we don't need that, but sims f and t, those are going to be our symbolic symbols that we're using. Here we've defined our function, and you just literally type Laplace of f, and it will give you the answer. So that's delightful. So in both cases, this one over here, we found our big U of s, and we needed to backtrack from big U of s to U of t. So we started with a little U of t, we did the Laplace transform, which took us to the big U of s, and then we need to go back, once we found the big U of s, to find our actual original U of t. So that happened here, and it also happened up here. So this process of going from big U of s to little u of t is called the inverse Laplace transform. We've kind of done it in a bit of a hand-wavy way. We did it using algebra. We did it by kind of looking at the table and going, well, I guess the little u of t must have been this thing in order to give us this big U of s. Usually we will just use Matlab to do that. It used to be that there was a whole, you basically do a whole course on how to get from big U of s to little u of t. Now you don't have to do that. But the thing that you might want to think about is, if I hand you a big U of s, how do you know that you can find a unique little u of t? So this is always the kind of questions that we ask ourselves. The answer over here is that if we have two piecewise continuous functions of exponential order and they have Laplace transforms u1 and u2, and it turns out that u1 is equal to u2 for s bigger than a, then we have that u1 is equal to u2. So the other way of thinking about this is, if you have two Laplace transforms that are the same, then you will get they will come. You have two. You will never end up in a situation where there are two different functions that will end up having the same Laplace transform. If you have a Laplace transform, it goes to a unique original function if you take the inverse Laplace transform. So a little bit of notation here. When we're unlaplacing things, so we're taking the inverse Laplace transform, we'll use L to the minus 1 in the same way that we use f to the minus 1 to represent the inverse of a function. Okay, so this is not 1 over the Laplace, it's the inverse of the Laplace transform. So you'll be happy to know that Matlab will find you the inverse Laplace transform. You would use it exactly the same way, almost as you did for finding the Laplace. Define your symbolic variables, put in the equation for your big U of s, so your Laplaced thing, and then you use inverse Laplace of f, and bingo, you get the solution. So go and try these out, just make sure that you're comfortable with that. So there are a few things to just kind of wrap up. I'm going to pause this video in a bit to give you a chance to kind of work through this before we head into the last phase. There are some sort of terminology things that we won't use a huge amount, but if you end up working in any field that uses Laplace transforms, will get used. So when we're talking about kind of the differential equations that we originally have, which usually are looking for a function of time, we say that these are time domain or the t domain, and that's all those functions that are expressed with t as the independent variable. And if we're thinking about the functions that have been Laplaced, if you like, so they're functions of s, we call that the s domain or the plus s domain. And sometimes we'll think of it as the frequency domain. why might we think of it as a frequency? Well, if we look at our ODE here, which we solved, and it has its S-domain counterpart over here, we can think about the parameters that so the variable that we have in our Laplace transformed version. So over here, if you think about it and you go and do a little bit of kind of working around of things, you'll see that S must have kind of units of inverse time if time is what's being measured in your original ODE. So we think about inverse time as being a frequency, and so we end up thinking of the Laplace transform as kind of living in the frequency domain. So we think about that as kind of like a frequency. It's not exactly the frequency that you know, but it's sort of ish because it's got units of 1 over time. So there's a lot more to Laplace transforms that we could talk about, but we're not going to. If you're interested, you should certainly have a look at the textbook. We're going to solve another ODE, and this one is non-homogeneous, and after that we're going to take a little bit of a break. So maybe you want to take a pause here and see if you can solve this one, and then come back and check the answer. Otherwise I'm just going to go straight ahead. Okay, so we take the Laplace transform of both sides. So we need to have the Laplace transform of u prime of t equal to 3 times the Laplace transform of u of t plus the Laplace transform of 6. And we've got an initial condition of u of 0 is equal to 0. So using our equation for this, we have this is s of u of s minus u of 0 is equal to 3 u of s plus 6 over s. So I just use the table here. So that should be an s. Let's tidy that up. And our u of 0 is equal to 1, so that goes to 1. So we have, if we do some, so this would be a big U, whoops, big U, little s is s plus 6 over s minus 3. And either plug this into Matlab, or if you're feeling brave, do partial fractions. And the answer that you'll find is that u of t is equal to minus 2 plus 3e to the 3t. So you could, of course, have solved this in one of the other ways that we've learned, because this is linear first order, so we know how to deal with those. And you might want to do that just to practice and check that you get the same answer. So this is kind of, we did this example so that we could see that we can use Laplace transforms to solve non-homogeneous differential equations. So where do we head after this? Now we want to think about when we've got discontinuous forcing functions. So over here, our forcing function was a constant, it was continuous, but now we want to think about those cases that we talked about at the beginning, where, for example, our forcing function does something like this. So it starts out at 1.5 and then it goes to 2.08 at 12 seconds. So this is our R of t. Those are the kinds of things that we're going to look at in the next video. But for the moment, just get comfortable with finding the Laplace transform, using the Laplace transform to solve simple ODEs. Don't get too stressed about finding the inverse transform. Either use Matlab, or if it's straightforward enough, just look on the table and kind of figure it out from there. All right.